you probably want one or the other. And you can think about I'm going to talk about here with the objective function in a minute. Usually we're working with profits and costs, like money that we're bringing in. So obviously we want to maximize profit and we want to minimize costs. Okay, so that might be helpful for you to think about. So here are the steps to linear programming. They're up at the top and they have the check marks. Okay. Step 1 is all brand new to us. We didn't see the objective function yesterday. Above objective function, I'm going to write the word goal. An objective is a goal. What's our objective today? What's our goal today? Okay. So the objective function is going to describe the quantity that you are maximizing. So the quantity to be maximized, which that would often be profit, or minimized, which would often be cost. So that's going to be brand new. We'll kind of see that. You'll be able to kind of tell what it is when you read the problem because it will give you either information about costs or profits. All right, next up, you're going to set up, I mentioned this yesterday, they're called constraints. They are those inequalities that we worked with Logan on or that I read to Jillian from the homework. Those are the things that limit you in the real world. Okay. After you set up the constraints, you're going to graph the constraints. When you're graphing constraints, that's when you think about solid or dashed, shade above or below. Okay, you're finding that, we call it sometimes the feasible region. So it's where all the solutions are. These are all the points that could work. Okay. And then after you graph the constraints, you look at your shaded region and you find all of the vertices. So just remember, vertices are points of intersection around the shaded region. You don't have to do all points of intersection, only if they are around the shaded region. And all of this, these 3 bullet points, this is all yesterday and earlier, like when we were graphing inequalities and solving systems, right? So we've been working on that all chapter. So that's not new, but this isn't always very easy, right? Like Logan's question, sometimes it's hard to find the constraints. Okay, so back to the new parts. After you do all this graphing and this finding of vertices, this has been proven for us. We're not going to prove it, we're just going to know it. If a optimal value exists, so if a maximum or a minimum exists, it will happen at a vertice. Okay? If a maximum or a minimum exists, it will happen at the vertices. So you are going to test your vertices in the objective function. So that's new to us, right? Yesterday we didn't have the objective function for profit or cost. Now we're going to add that in, okay? And we just, we have vertices as x and y. We plug them in, and we'll figure out, what are all the profits for these different points. Pick the highest one. There's your maximum. If your objective function is all about the cost, you plug in the numbers, you'll get the lowest one as your minimum, your optimal cost. Okay. The last step is make a decision, and this one is easy to overlook, but you've done all this math and you've shown all this stuff. What you want to do with make a decision is report back. So when I say report back, it means you should manufacture or you should keep an inventory 200 of the laptop Model A's and 100 of the laptop Model B's, and you will make the most profit. Okay? Or like yesterday's example, you should mix 3 bags of brand X with 1 bag of brand Y, and that will cost you the least amount to give you all your minimum requirements. Okay? So you got to report back, like, what did you find? What should we actually do? Okay, so let's look at the first example. Okay. Now we're going to increase in difficulty in the amount of work we have to do. So do you see in my first example, I've done most of the work for you? Okay. Your objective function, let's label it, is this z equals equation. So label that so you know that's your objective function. Okay. The book, when it doesn't have any meaning, it'll just use z, a third variable. It doesn't matter what it is. Okay? Z is the thing you're trying to minimize or maximize, in this case both. If I'm doing profit, I usually put a P there. If I'm doing cost, I usually put a Z. So we don't even have to write the objective function. It's provided for us. We don't have to write the constraints. They're all listed for us. And they're even graphed for us. Now, I'm going to show you just really quickly. I'm going to label these 4 lines. So, like, x equals 0 is really the y-axis. So I'm going to label that. That's x equals 0. Y equals 0 is really the x-axis. So that's that line, the horizontal line. Okay. For x plus 2y equals 4, I would have used my intercept method. So the x-intercept is 4 and the y-intercept is 2. That must be this line that is decreasing. So this is the line x plus 2y equals 4. And then on x minus y equals 1, the x-intercept is 1, the y-intercept is -1. That corresponds to this line right here. Okay, so this is x minus y equals 1. I'm just doing that, like labeling those lines, because we didn't actually take the time to graph them, so that when we go back and we identify our vertices, we can make sure the vertices are right. Okay, so we know which line is which. All right, so everything is graphed for us. We have, I would call this little shape right here, this is called our feasible region. This is where all of our solutions are. Okay, these points work for all 4 of my inequalities. How many vertices do you have? Points of intersection around the shaded region. Looks like 4, doesn't it? It's a quadrilateral shape, so you should have 4 corners.
If you have 4 equations, will always be 4?
It depends on where the lines are intersecting. Yes, so you have to be careful. A lot of times it is, but it doesn't matter. It depends on where the lines are intersecting, but it also matters like where the shaded region is. So if I found out that the shaded region was just like right here, then I would have 1 and 2 points of intersection. Good question. But if you notice that it's like a closed shape, so this one is bounded on all sides, right? It's like stuck in that little closed shape. You have to have as many vertices as sides that you have to that shape. So that's a quadrilateral, so I have 4. Okay, some of them are easy, right? Like V sub 1 is really 0, 0. That's obvious. I don't really need to check that one. And if I had graphed the line x plus 2y less than or equal to 4, I know that V sub 2 is that y-intercept 0, 2, right? So I know 0, 2. V sub 3 looks like what on yours? 2, 1. That would be one where I would just verify that one. That's the intersection of the 2 slanted lines. So if I put 2 in for x and 1 in for y, does it make both equations true? 2 minus 1 is 1. 2 plus 2 times 1 is 4. Yeah, so that's on both lines. It's the correct intersection. And then this one, this would have been the x-intercept for the line that is x minus 1 equals y. So I have 1, 0 there. Okay, so you got to find all the vertices. We kind of got to jump ahead because we had done all that work. After you find the vertices, what do? Test them in the objective function. So what that means is, like up here is my objective function. If I'm testing 0, 0, I'm doing z equals 3 times 0 plus 2 times 0, which is 0. So z equals 0. If I'm testing 0, 2, 3 times 0 is 0 plus 2 times 2 is 4. If I'm testing v sub 3 equals 2, 1, 3 times 2 is 6, plus 2 times 1 is 2, so z is 8. And on this last one, z is 3. Okay. If a maximum or a minimum exists, it will occur at the vertices. Since this one is bounded, you know for sure you have one of each because it's closed. So there's a lowest point and there's a highest point. Which z value is your lowest? 0. So you would report back. You have a minimum of z equals 0 at 0, 0. This doesn't really mean anything to me, so I don't have a lot to say in terms of labels. And which one produces your maximum z value? V sub 3, right? Your highest z value is 8. So you have a max of z equals 8 at 2, 1. Now, I could use v sub 2 or v sub 4, or I could use like even the point 1, 1 right in the middle. It's in the shaded region. Those are all valid solutions. They fit all of the constraints, but they are not optimal. They don't give me my max or min z value. Questions about what happened? These are not my favorite because they're just like numbers and they don't mean anything. So I find them kind of boring. Yeah. It's good for getting like the ideas down. Let's look at the next one. Okay, I think I have y greater than 0, greater than or equal to 0 on that one. Okay, let's graph the lines together using the intercept method. Start with the first one. What's your x-intercept? 4. Y-intercept? 2. Plot those 2 points for me. X-axis 4. Y-axis 2. Solid line. Would you be shading above or below that line? If you test 0, 0, is 0 greater than 4? No. So don't shade where 0, 0 is, you shade above. Okay, line 2. X-intercept at 7 over 3, which is like 2 1/3. So a little bit past 2. And y-intercept at 7. Plot those 2 points, solid line. Would you shade above or below? Above. Test 0, 0, 0 is not greater than 7. So 0, 0 again should not be shaded. Now my overlapping shaded region is kind of like in this top right area. Next one, x-intercept at -7, y-intercept at 7/2, which is 3.5. solid line. Shade above or below? Below. If you test 0, 0 on this one, is 0 less than 7? Sure enough. So now I'm shading kind of like over here on the right side, in this area right here. I got one more equation to go. Y equals 0 is which axis? The x-axis. So I'm drawing y equals 0, and y's that are greater than 0 are above. Okay, so now my shaded region. Just keeps going, right? Okay, any questions about graphing? Okay, now we want to pick out the vertices. This is an example where we have 4 lines, but because our region is unbounded, like this side doesn't close, I have only how many vertices? 3. Those are the corners to the shaded region. There are other points of intersections, like for the lines, like here and here, but because they're not next to the shaded region, they're not considered vertices. Okay, you guys help me out because your graphs are always better than mine. What do your vertices look like? 1, 4? Okay, that would be my V sub 1. And that would be the intersection of the third one we graphed. -1 plus 2 times 4 is 7. And the one with a y-intercept is 7. So the second one we graphed, 3 times 1 is 3 plus 4 is 7. So yeah, that is the intersection point. What else looks like a good intersection point for you? 2, 1. That looks like my V sub 2. And that's the intersection of the first one. 2 plus 2 times 1 is 4. Yeah, that works. And the second one, 3 times 2 is 6 plus 1 is 7. So yeah, that's the point on both lines. And also, what's that last one? 4, 0. Okay, 4, 0. Which, that one we can agree because we have the y equals 0, and then that was the x-intercept at 4, 0. So we know it's touching the x-axis right there. All right, find your z values, right? You found your vertices, plug them into your objective function. The objective function changed. It's now 4x plus 2y. So in this one, I'm thinking z equals 4 times 1 plus 2 times 4. So that's 4 plus 8, which is 12. 4 times 2 plus 2 times 1, z equals 10. And then z equals 16. Okay, any questions on where I got my z values? Okay, you gotta be careful here. This region is unbounded. Okay. So think about all the solutions that are getting shaded. It looks like right now with my z values I could pick a min and a max, right? But all these points in this shaded region, and it just like continues off my board, these are all solutions. So like let's estimate, like I don't know, what do I think this point out here is? I think that point out there is like, I don't know, probably 10, 15, 4. You know, who knows, right, what that point is. But that's a point in the solution set. What happens to your z if I put in 15 and 4? It's even bigger than 16, right? And imagine this like keeps going out here. Couldn't I pick like 100 and something? And then it would be even bigger. So what can we say about this particular unbounded region? There is no maximum. And that's very specific to this unbounded region because all of the x and y solutions are going to be positive x and positive y. The unbounded region is in the quadrant 1. So then when you put in positives here, they just get bigger and bigger. So actually you have to be really careful with an unbounded region. Sometimes it may not have a maximum or a minimum. Sometimes it might just be missing one of them. This one is definitely missing a maximum. Okay. As for the minimum, you kind of got to reason through this. We definitely have a minimum in the z values that we checked, right? Z equals 10. So our question is, are there any points out here in this shaded region that are going to be less than that? No. Because all the points out in this shaded region have x's that are positive and y's that are positive. So they're getting bigger and bigger. If I had left off that y is greater than or equal to 0, if we had shaded down into the negatives, then that may be a case where there is no minimum. Okay, because then you could put in a negative value and that would drop it lower and lower each time if we put in like negative 100. But on this one, I would argue because all these x's and y's over there are going to be positive, that this is a minimum. Okay, you have a minimum of z equals 10 at 2, 1. So the only time you really ever have to contemplate that is when it's unbounded. If it's bounded, if it's closed, you will have both for sure. If it's unbounded, maybe you have one but not another, maybe you don't have either. Because you're doing most of your linear programming is like with reason, right? It has like a word problem that goes with it. You're usually up here in quadrant 1. So you would have one or the other. Okay, let's do the problem on the back. I want you to skim it. Read it. Try and get a picture of what's happening here. And as you're reading it, I also want you to think about what are your unknowns, because we're going to assign variables here in just a moment. So what are your unknowns? Okay, when you read that last sentence, find the number of units of each model. That's what you want to find. Those are your unknowns. So what variables do you guys want to use? For a reason? So then what do you want to use? Next one. Okay, so we'll say X is the number of 250 models, and Y is the number of $400 models. Are we okay with that? Let's start by writing the objective quantity. So this one is new. Remember, the objective quantity is your goal. What's your goal in the end of this? You, the business owner. Maximize your profit. So my objective quantity, I'm going to say my profit equals, and then I'll go searching for, what do I know about profits on X, $250 models? Profit is 45. So for every X model I sell, I get $45. And what do I know about profits for Y? They are 50. So if I add up all my profits from my 250 models plus all my profits from my 400 models, those would be my total profits. Okay. Save the objective function for later. Now you got to write constraints. Okay. So what things are limiting us? We want no more than $70,000 in our inventory. So is that a greater than or a less than? That's a less than or equal to 70,000. And to do the price for my inventory, then I would use the prices on the models, right? So the X's are priced at 250 and the Y's are priced at 400. So I want to keep my inventory to $70,000 or less. What else limits you? Demand for tablets. We don't want to keep more than we're going to sell. It says we estimate that we will not sell more than 250. So use a less than or equal to, and what would we say on the other side? All the models together should be less than 250. So X plus Y. Anything else limiting you? No, just real world stuff. So we should add X greater than or equal to 0 and Y greater than or equal to 0. Remember, those are like hidden constraints. Since they didn't give me a minimum already, I do know that my lowest possible value is 0 on those. Okay, so let's graph. If we had used L and Q for variables like you wanted to, you would just assign either one to L or Q, but we'll use X and Y and assign them appropriately. Okay, let's do our intercept method. This one's real awesome. I love X plus Y equals 250 because my X intercept is at 250 and my Y intercept is at 250. That's easy, right? Can you guys help me out with a calculator here? What is my x-intercept for this top line? If I put 0 in for y, I have to do 70,000 divided by 250. 280. And then if I put 0 in for x, what's 70,000 divided by 400? 175. Okay, I like to, on a linear programming problem, because like I'm going to get these big intercepts, I like to do my intercepts first so that I can then decide like my scale. You know, I got to go up to 280 and 250 on the x and the y, so I'm probably going to scale by 50 or 100. It doesn't have to be like super tiny and super accurate, so don't waste all your time on that. Okay, so I'm going to scale by 50s, and I'll just mark, I'll go, there's 50, there's 100. There's 150, there's 200. There's 250, there's 300. Don't overdo it, right? And then I'll do the same thing on the y. You can have different scales on x and y if you're using the intercept method. If you're graphing by slope-intercept form, you got to be really careful. Okay. So plot my intercepts. 280 is on the x, and 175 is on the y, and draw a line. Test for shading. That's 0 is less than 70,000 for sure, so I would be shading towards the origin. And then plot my 250s. Draw a solid line. test my shading. 0 is less than 250, so I'd be shading towards the origin. I have a bounded region. V1, V2, and V4, those are pretty easy for me to identify. And one is the origin. And then V2 and V4, those are the intercepts I graphed. So like I know for certain where those points are. The one point that like maybe I'm unsure about is my V sub 3. So that's the intersection of the two lines, 250x plus 400y equals 70,000, and x plus y equals 250.
X-intercept at 175.
That was a y-intercept. Its x-intercept was at 280, and its y-intercept was at 175. If you labeled your variables differently than mine, yours could be flipped. But if you labeled x and y like me, I think I graphed it correctly. Is there anything else like maybe I did wrong? Please stop me if I did. Okay, so I'm talking about V sub 3 right now. This is the intersection of the two lines. So I'm going to say like, was it 250x plus 400y equals 70,000? Okay. And the other one is the x plus y equals 250, but I'm going to solve by elimination. So I'm going to multiply that equation by negative 250. So that would be negative 250x minus 250y equals negative 62,500. And that'll be 150y equals 7,500. So y equals 50. And then that's really easy if I plug back into that x plus y equals 250. If y is 50, then x is 200. So there I'm using my knowledge from earlier in the chapter. Like, what's that point of intersection? Solve the system. You can do substitution, but I love elimination. So I did elimination. Okay. You can see like my graph was not really drawn like accurate, so it doesn't really look like it's at 250. Okay, so it's good for you to just like maybe solve that system. Okay, last thing is after you find those 4 points, then you need to test in your objective function. Okay. So for like V sub 1, V sub 2, V sub 3, and V sub 4, I'm testing in the P equals 45x plus 50y. Well, which one is definitely not going to maximize my profit? 0, 0. Okay, this is the minimum of the bounded region, right? So I'm not even going to test that one. But I don't really know which of the other ones work. So like for V sub 2, I would do the profit equals 45 times 0 plus 50 times 175. And that one is 87.50. And then for V sub 3, I would do the profit equals 45 times 200 plus 50 times 50, which that one is 11,500. And then for V sub 4, I would do 45 times 250 plus 50 times 0, and that one is 11,250. Which one maximizes my profit? The V sub 3, right? So if I want to maximize profit, here's where I make my decision. I gotta report back. Okay. So my answer is stock 200 of the 250 models and 50 of the 400 models to maximize profit. And if you were asked, the max profit is $11,500. Okay, but my decision, what I'm reporting back to that store owner is, those are the number of each tablet that you should keep in your inventory if you want to sell the most tablets, make the most money. It does not always happen at the intersection of the two sloped lines. Sometimes it often does, so sometimes people always just say that's the vertex that works. But you really do have to plug them into the objective function. Sometimes the intercepts are the ones. Like, you shouldn't even have the $250 model sometimes. So you have to actually plug it in and check it. Okay, so you've got a few more problems on linear programming. Maybe you need to finish up some of the inequality stuff. It's really the same idea, just with the objective function, the testing, and the reporting back added in. Okay. Tomorrow, there's no new information. It's practice with linear programming. So we get a moment to breathe and see if we can do these problems on our own.